Okay, so our second lecture of the unit. Today we'll be covering navigation structures, graphs and graph structures. So a part of searching requires that we have some kind of way to characterise our environments. We do this with certain structures which are called graphs. And those structures then allow us to characterise the environment in different ways so that there is a logical transition from one location to another in a search function. All right, so last week we looked at some basic concepts of traditional AI. So we looked at such things as sensors, actuators, agents, what is a rational agent, what do we mean by performance, the idea of a goal. Now, the idea of a goal here will be very important for pathfinding because pathfinding is really a kind of program that considers a goal, which is a destination location, and then tries to solve the problem of finding a path or a shortest path between 2 points. Problem-solving agents, policy and optimal policy. Then we also talked about, from the perspective of game AI, that is where we're developing for in the industry, such things as avatar, player, non-player characters, game states, and so on. What we'll talk about this week, we'll be looking into the concepts around a game environment from a very mathematical standpoint, and we'll be looking at how we can characterise the environment in sort of abstract ways using discrete structures. In particular, we'll be looking at graphs and weighted graphs. And then we'll also look at waypoint graphs and grids. And we'll begin to look at the problem of pathfinding, but it won't be completely done this week. There'll be more that comes the week following. So we'll look at the heuristic functions and the greedy search algorithm, and then also the A-star search algorithm. So from an architectural standpoint, when we look at the game engine, pathfinding is done somewhere here. It's actually done in the simulator. So the simulator will first of all do that calculation. Once it's got a path, it will update the games. Once it's got a path, it will move the character, and each time it moves the character along the path, it'll do an update of game state, and that information comes back to the simulator and so on. So, stated here, actions are represented by messages sent to the simulator from an agent's character's controller. As the agent is moving, the controller is telling the simulator that it's moved along the path somewhere, the game state is updated, that information is then passed back to the controller and the simulator. So the controller might send a message to the effect, move a certain agent I from position X to position Y. So a really good example might be you're doing a point-and-click game, and the controller is your standard controller that you might have, for a console game or something like that, and you've done a point and a click, and now the character has a goal location where it needs to move to, and so this is that scenario. The same scenario is implemented in other ways in other kind of video games. It's just that the information isn't a point and click, it's just coming from some other source. So the goal is not always a point and click. It could come from some calculation being done in the game. So then the simulator indexes character I, passes the start and the destination positions to a pathfinding procedure. And then the simulator does the following. It initiates animation for the character, moves the character along the path, and updates the game state variable as it does so. All right, so that is basically the story of what happens at a software architectural level. But to understand the search itself and the algorithm used to actually find a path, we need to start to get underneath the thinking behind solving that problem. And one way that we can do this is we can characterize the problem, in some sort of structured way. And one very common structure in mathematics for doing this is what's called a graph. So a graph is defined this way. It's an ordered pair. It's a pair of sets V and E, where V is the set of vertices. And so that is basically all of these nodes. These are the vertices, or nodes. And E is the set of vertex pairs called edges. So you can see whenever we have two vertices as a pair, it's the same as saying these two vertices are connected with each other. So if x and y is in E, then x is in V and y is in V is pretty much a standard rule for a graph. All right, so what are vertices and nodes? So just to, for those of you who are not familiar with some of this mathematical speak or notation or terminologies, strictly speaking, a vertex is an element of any discrete ordered set V. So what we're really talking about here is we've got a set of integers. An integer set would be a discrete ordered set. And that's handy because on a computer, we're always pretty much dealing with integers, so it's very easy to represent vertices that way. So, as stated here, V may be a subset of the natural numbers, again, integers. V may be a discrete subset of vectors in Euclidean space. V may be anything that is a discrete set. So you can sort of extend this idea of a vertex or a node into all kinds of other software concepts. So you can see here what I've tried to do is begin with a mathematical concept, and now I'm talking about things like discrete subset of vectors, Euclidean space, and sort of you can see that how that might move into something that could be implemented in software. From a software perspective, a node is a data structure that represents a vertex. It's labels and, in some cases, adjacency in a graph like data structure. So how many people are not familiar with this idea of a node in software? Has everyone done discrete structures? Okay, so basically a node is defined as a structure, and in that structure you have some data that you want associated with that node, and in addition you'll have maybe a list of other nodes this node connects to. Right, an edge is simply a relationship between two vertices. So that is that E is really just a subset of the cross product of our vertice sets. And as stated here, if x and y are elements of V, then that tuple x and y implies an edge that connects x to vertex x to vertex y. So if the graph is undirected, it doesn't matter the order, but if it's directed, then x is connecting to y. Okay, so that's all great from a mathematical perspective. We've got this idea of mathematical graph. It's an abstract idea, and soon I'll show you how we can actually write algorithms and do searches over structures like this. But how does it relate to a 3D virtual environment? What is the connection between this strange abstract thing called a graph and the world that we are accustomed to in our virtual games? All right, so there are different ways that we can look at the environment. Initially, because everything in a 3D environment is a Euclidean flat space, we already have a natural partitioning of that space. So we can already naturally, without doing too much effort, we can partition that space fairly easily up into a grid space. But just simply by the virtue that, for example, this corner here might be 0, 0, and each step along would be an even distance. And so knowing the step distance and where the origin is, you could determine the coordinate of any other point in this grid through some fairly simple calculation. So in a virtual environment, we might partition the space into grid elements in either 2D or 3D is one possibility. So in Unity 3D, that obviously doesn't make any sense. What have I written here? You may what? In Unity 3D, you may have a conceptual flat surface defined by the XY plane at, say, y equals 0. A grid is something that is then implied. We don't have to explicitly define this grid. That is, we don't have to actually allocate any data for this. All we have to do, we don't have to allocate very much at all. All we have to do is know where the origin is and know what our step distances are. So that's what I mean here. A grid is something that is implied. It's an implied structure on the surface. We can define the grid as a regular subdivision of this XY plane and a cell at some multiple of steps in either X or Z from the origin. All right, so now that we know how to define a grid, it needs to be generalized in a way that we can get a graph out of it. So a grid can be generalized really simply. What we do is we simply take the center point of a grid element, of each grid element, and that is our vertex, or that is the location of our vertex. And the adjacency relationship between grid elements can just simply be, can simply define the edges. So in this case, you can see that there's edges that are simply joining the center of each of the grid elements just simply by adjacency relationship. And it basically forms a lattice graph. Right, so if all grid elements have equal dimension and all sides of a grid element are equal, then any grid element can be identified by just its center coordinate. The side length can be defined as a single global variable d. So the idea is that if we know what the length of the side is, some value d, neighbouring grid elements can be found at some multiple of d away from each dimension. So if we want to know, if we know what this vertex is as a location, we can just simply add multiples of d in any direction that we're going, and we can, as we go along, compute what the coordinate is of this new vertex. We don't have to actually store data to do it. All right, so this is kind of important because when we do searching, we have problems of complexity. And this is no different for pathfinding searches, even though in most games pathfinding is fairly quick now. You don't have to wait very long for a routine to return a path. There is issues of complexity. So when we look at how we represent the space, we need to consider this complexity to some degree. For example, if we look at a grid, oh yeah, okay, so as stated here, if we're looking at using a grid and we're after a path, and once we've got this path, we might actually put some smoothing on it, then we don't need to have a lot of detail in the shape of that pathway. So, for example, what we mean by our neighbourhood might just simply be those that are directly adjacent to a particular node. So in this instance, we'd be looking at the 4 that are coloured blue around the particular node given by x and y. Now, the reason why I'm saying that if we have smoothing is because if we take this sort of relationship of our neighbourhood and we try to find a pathway with that sort of neighbourhood relationship, pathways will tend to have very sharp bends like that, okay? They won't go diagonally. And because of that sharp bend, you might be inclined to try to smoothen that pathway out once you have it. Alternatively, we could get smoother pathways if we considered diagonal adjacencies as well. Now, the problem here is, in a search, every step that we take is only dealing with a neighbourhood of 4. So in the first step, it's choosing from 4. In the next step, it's potentially choosing for 4 times 4. In the next step along, it's choosing 4 times 4 times 4. And you can see that the complexity is increasing. The more steps away, the search space is actually getting up to 4 to the power of n if we consider n steps away. Hopefully I've got a pen with me so I can explain that on the board as well. Yep. So if we have an initial position and we have 4 neighbours, then each of those neighbours again will have 4 neighbours, and you can see that structure is growing in complexity. And this is 0. This is step 1. This is the pathway of step 2. Again, 4 neighbours. You can see that this tree is going to keep growing and growing, and so the complexity of our problem grows exponentially with how many steps we want to take along a pathway. So if we choose 4, we have a much smaller tree that we have to search than if we choose 8, for example. It's much maybe more efficient to search a tree where we only have 4 to the power of 0, 4 to the power of 1, 4 to the power of 2, right? This is really the pattern that's going along, as opposed to 8. If we had 8 to the power of 0, 8 to the power of 1, 8 to the power of 2, all right? 8 to the power of n will probably be something much, much bigger than 8 to the power of 4. So decisions like this become very important when doing pathfinding. Well, actually doing any kind of searching in AI. The complexity of the problem has to be well considered. All right, so now we'll talk about pathfinding and searching. In particular, we'll be talking about going back to these abstract structures that I was talking about before, the graphs, and what kind of algorithms and the implementation of those algorithms for searching in a graph. So basically, having characterised a virtual environment, for example, with a grid, you can see that we can very easily arrive at a graph. This is also true for things like navigation meshes. Navigation meshes can also be converted into graph spaces. And also, well, obviously waypoints is a fairly clear graph structure. All right, so understanding that we can always arrive at a graph, we need to look at what graphs, we need to look a little bit more at graphs and how we actually do searching in graph spaces. So the first concept I'm going to introduce is what's called a weighted graph. And this is one where every edge is coloured with a weight value. All right? So this word coloured in mathematical terms just simply means it's assigned a value. And that's actually got historical context. So there was a problem called the three-coloured mapping problem. So the idea was, let's say we have a map of Germany or the map of Europe. How can we colour the different countries so that, how can we colour the different countries, or what is the minimum number of colours that we can use to colour every country so that no two adjacent countries have the same colour? That was a very difficult problem to solve for a long time, and so this is why in mathematics we use the word colour to represent values assigned to objects in graphs. Just a bit of history there. All right, so this is what a weighted graph looks like, and this is the kind of problem characterization that we're interested in. We have a certain starting point in the graph, we have a finish point or the goal, and we might be asking the question, you know, what is the minimum cost pathway from the start to the finish? And what I mean here is that if these weights imply a cost, what is the pathway that is the minimum cost? So generally, when we consider pathfinding, we're trying to optimize some cost function. So this often has to do with optimizing search as well, but you might be interested in your character walking along the shortest pathway because it might look a bit silly for your character to walk in a long, convoluted pathway. So the fundamental problem here is really optimizing a cost function in order to find a path. So these two things go hand in hand in our pathfinding problem. Just as a heads up too, when I talk about pathfinding here, this is very characteristic of what we do all across AI when we're doing searching. We're always trying to optimize some cost function in doing the search. So it's not just applied to pathfinding, it's applied to all sorts of things. It's applied to planning, it's applied to game tree searching for board games. So all kinds of searches are looking at optimizing cost functions. So we're looking at the problem of pathfinding is basically to solve searching for a cheapest path. There are a number of ways that we can do this. The most obvious way, and I think you've all seen this if you've done discrete data structures, is brute force, the idea that we can just simply implement a logically straightforward algorithm that doesn't have any kind of optimization in it and just try every possible pathway. So basically going down this pathway first and then maybe this pathway next and then this one next and so on, and then trying every possible pathway until eventually we find the shortest path. Or we could do it as a depth-first search. We might go through these ones first, and have we got to N yet? No. And then we look at the next layer and the next layer until we eventually arrive at N, and then maybe we get some optimization by not looking at the pathways that are longer than N. So brute force method is one approach, but in game programming, it's far too expensive. What we want to do is we want to have methods that are significantly faster and better performing than a brute force. And one way that we can arrive at such algorithms is basically to do with what's called heuristic functions. So what a heuristic function is, because one of the problems that we have with searching, or with any kind of search program, is that if we knew what the shortest path was a priori, or if we knew what the optimal cost path was before we started running the method or the function, we wouldn't have to run the method, okay? So we've got a kind of catch-22 here. We've got a conundrum. We can't know the pathway before we found it. So we don't actually have complete knowledge before we start a search. This is why we need to have what's called a heuristic function. A heuristic function is a kind of guessing function. It's a way to sort of have an informed guess about how far away or in which direction the search should go if it should find an optimal pathway. So in this case, heuristic function Hn estimate cost of the cheapest path from node n to a goal node. So the aim here is to actually do better than a brute force search by making some educated guess. As stated here, it's a kind of educated guessing function. Right, so searches that have heuristic functions are what are called informed searches. They're informed searches because we as human beings can sort of reason about the problem to a degree, and then, arrive at some good way of guessing. And then when we implement that way of guessing as a heuristic function, we've kind of given that search information that it couldn't have if it was just a simple brute force method. So it's sort of surrogate information that coincides with the problem. For example, with pathfinding, if we are at a certain location and we want to get to another location, just simply a beam line or a straight line from one location to the other could be a very good heuristic. All right, so I'm going to introduce what's called the greedy search algorithm. The reason why I'm using greedy search rather than just simply some best first search statement is because greedy search has a fairly long history in AI. It's a really simple kind of program. I don't have, here we go, no, that's not it. Don't have a board cleaner, do I? Okay. Oh, yes, I do. Here we go. It's got a long history because, firstly, in many cases, a greedy search, it's really simple, and yet it can often give optimal solutions to a problem. So the greedy search algorithm actually started out as what is called the backpack. It actually started out as a solution to what is called the backpacker's problem. And the backpacker's problem works this way. You've got a backpack, okay? I don't know. I'm not very good at drawing backpacks. All right, you've got a backpack. You've got a bunch of items. All right, you've got one that's, say, 1 kilo, and you've got one that's 5 kilos, another one that's 500 gram, and maybe we've got two that's 5 kilos. Anyway, we've got a bunch of items like this, some big, some small, And the question is, I can only, say, carry 20 kg, for example. Maybe I need to have some that are like 7 kg and some that are 9. Right. The question is, how can I pack this bag so that I get as close to 20 kilograms and as most items in that bag possible. So I want to optimize my load so that I've got as many items in there as possible and it reaches as close to 20k as possible. And so one way to solve this problem is with the greedy search algorithm. That is that we take the largest object first and we stick that in. And then we calculate how much we've got left. So that would give us 11 kilograms. And so then we take the next largest item smaller than 11 kilograms, that's 7 kilos. Then what have we got there? We've got 16, so that leaves us another 5. So we can put 5 kilos in, and that will bring us right up to 20 kilos, and we haven't wasted any of our limit. So that solves the limit problems. That solves, or it gives a very good solution to making sure that we've actually got 20 kilos in the bag, and we don't have something less. The other way around is if we want to have as many objects in there as possible, we start with the smallest objects first. We stick a 1.5 in there, and we keep going up from lowest lowest weight to largest weight, and then you'll get as close as you can to 20 kilos with as many items as you possibly can stick in the bag. So this is the kind of optimization that comes out of the greedy search algorithm. The same thing can be done for pathfinding. You can use a greedy search that we'll basically try to select the best options first on the assumption that if our heuristic function is really good, if it's really, really good, then we'll probably get an optimal pathway out of the greedy search algorithm. So here Hn is the cost of choosing node n from the current node. So if we actually, I wonder if I've got it on the next page. Yes, I do. All right. So it's the cost of choosing node n from the current node, and it basically just simply chooses the cheapest one. In the same way as we chose the lightest one if we wanted to pack as many objects in the bag as possible, or the heaviest one if we wanted to get as close to 20 kilos as we could. Here what we're doing is just simply choosing the cheapest neighbour, or the cheapest neighbour, sorry, the neighbour with the cheapest edge connecting it. So the greedy search basically tries to minimise our heuristic function. All right, so just to describe what happens here with this algorithm, I'm going to step through what the greedy search actually does when it's doing a search. So I'll probably go back to that. This is the graph that we're dealing with here, and the greedy search, as it goes along, it will choose the cheapest one, 0.2, and so on. Now, I've actually got a graph different from that. I've taken out the edges around this node so that we actually have a dead end, so you can see what happens with the search when it backtracks. And it's important that we're able to do what's called the backtrack in the search, because the search isn't always going to succeed in finding the goal. And if it can't succeed in finding the goal, it has to backtrack and then it has to find a different pathway. And so I'm going to introduce this idea of colouring and as a concept to step through this search. But it's also something that you can consider in writing programs as well. You want to, when you're searching, you want to be able to keep a record of where you've been so you don't repeat that location a second time around. So I'm going to use two colours in this explanation. I'm going to use blue for forward track and red for any backtracking. So basically from the start root node, the search paints the edge to the lowest cost child. That's this one here. What we notice here now is that we've come to a dead end. We can't actually go any further in our search, so we actually have to do a backtrack. So now I paint it red because we've backtracked, and it chooses then the next cheapest node, which is the next cheapest edge, the node with the next cheapest edge, which is an edge of 0.3. We're also looking for certain conditions in the search. So the search has two backtrack conditions. The first one is that the child node n is a leaf node. That is the case here. We've got a leaf node, or basically a dead end. The child node n has been painted already. So that would be, for example, if we took another pathway and we came back and we found that this node had already been painted blue or red. Then we need to do a backtrack. So under these two conditions, the search will then backtrack and paint the edge to the next most cheapest child node. So what happens is after a series of best first searches, so it's gone 0.3, and from this place it can choose 0.2, 0.1, 0.04, so it basically goes around and finds a path. And once it gets to the goal, it's succeeded in finding a pathway, so then it returns that blue path. It's fairly simple. Where a brute force search would have looked at every possible pathway in order to find a shortest cost path, the greedy search algorithm has simply applied a best first packing in order to arrive very quickly at a pathway. Now, what we'll notice here is that the pathway is not necessarily the cheapest path. It's not the worst path either. It could be. Sometimes the greedy search will actually return the worst path. But if our heuristic function is good, if we've really considered our heuristic function for the problem, it should return a good path, a pathway which is as good as the heuristic function is at measuring the optimality of that choice. So we get a pathway, but it's not the cheapest one, but it's not the most expensive one either. And well, if you think about video games, a player isn't really going to be that fussed if the character is taking a bit of a longer pathway, okay? I mean, most players don't really pay that much attention to the character unless they're there interacting with them somehow. For example, if a soldier is right there shooting upon them. So how that character got there is not necessarily always important. So in this case, we have this really fast method through a greedy search algorithm. It doesn't always give us the most optimal pathway, but it gives us a good pathway. Right, so this is the pseudocode for that. So this will be important for our workshop coming up next week. We'll be starting to look at pathfinding. Not this week. This week we just have the simple rotating box example. But next week we'll start to look at pathfinding. So this is a pseudocode for it. I can step through it here. It's pretty much everything I've just shown you. But basically in software, we have a root node and a goal node. That's the input to our search. And we're starting off with an empty path. And what we want to do is actually return that pathway filled with some nodes or some edges. So we begin looking at children. So that is, we begin looking at all of the. So this. Actually, I need to clarify something here. This is actually for searching in a grid space. You can use it for any kind of graph, actually, but we'll end up doing it in the workshop on a grid space. So the children here are then sorted in ascending order. And the reason why we're sorting it is because it's greedy, so we want to get the least weight one first. And then we go through the sorted list of children, and we take the first one, and then we ask, is it painted? And if it is painted, firstly we ask if it's painted. If it's not painted, then it gets painted. And then we ask, is that child already the goal node? So have we already arrived at the end of the search? If that's the case, then what we want to do is we want to backtrack. That is, we want to unwind the search and gather the pathway together. So here I've got a path which is being updated with the path before and the union of the new child. And that then gets returned. Now this method here is actually a recursive method. So you can see greedy search here and greedy search being called within itself. There's some real problems with recursive methods, and you'll find out what those are when it comes to implementing this function. So basically, once we've found the pathway, if that's returned, this recursive step will return the path, and if it's not empty, it'll keep doing this return. That is basically, it'll unwind back up through the recursive step. But going forward, what will happen is it will try out each of these children, and if it's not the goal node, it will call this method again, and it will pass in that child as the new root, and the old goal and the path, and it will simply repeat this step on the child as though the child was the root. Eventually, it arrives at the goal node, and then it unwinds back through and returns the path. Any questions on that? Everyone sort of clear on that explanation? All right, so painting an edge, what does that mean in terms of software? So there are different ways that we can do that, and each different method sort of has its own benefits. So the notion of painting edges or vertices describes any method to keep track of visited nodes. Okay, so if the graph is something really small, say it's only got a couple of hundred nodes in it, you could just use a bit set, or even if it had like 1,000 nodes, you could use a bit set just to indicate that a node has already been visited. If the graph is something really large, but the path will be very small, so you might have a huge search space, but you're only looking for pathways that are sort of local, then you could just use a list. So a list would be an easy way to keep a colouring of your nodes. So every time you visit a node, just stick that node into the visited list, and you just keep checking the list. Now the reason why I'm saying that if the graph is large but the pathway is small is because if the list gets too large, it might not be an optimal structure to search in. You might have to go through each element to find if that element matches a node that you're already looking at. So a list could be useful there. But if we're looking at much larger structures, so if we're looking at large graphs and also looking at large pathways, then we need to take advantage of the fact that we're dealing with a 3D virtual environment. And so we want to take hold of such things as quad trees and octrees. So is everyone familiar with what a quad tree and an octree is with respect to virtual worlds? So as I pointed out before, virtual environments have a natural partitioning. So if we think about a 3D space, all right, so we've got our X, we've got our Y, and we've got our Z. Well, there's a kind of natural partitioning to this space. So if we consider it like a cube, where are we? Down to here. All right. We can actually partition this space already into eight pieces, right? So I've got a cube, and we basically can cut it into 8 smaller pieces, and each of those cubes can be cut into 8 smaller pieces, and so on. So an octree, a quad tree is basically for a flat surface, but an octree is for a 3-dimensional space. We can keep subdividing it, and each of those ends up being a child under a root. So we have this whole area as the root, and then we can subdivide the space into 8 subspaces. 1, 2, 3, 4, 5, 6, 7, 8, and that would be all of those cubes there. And then we can subdivide those again. And this is really efficient to search, because if you want to know where something is in this space, if you want to be able to find a neighbour, so you've come across a vertex, you know where it exists in 3D space, you want to find if you've already visited it, you just simply take that vertex as a coordinate, and you just simply query, is it which one of these is it a subset of? And if it's a subset of this one, then you go down and you ask, all right, which one of its sub cubes is it a subset of? And you keep going like that, and very quickly you arrive at a data storage which either has a vertex there that you visited before or it doesn't. So quad trees can be very efficient when you have very large spaces and very large graphs, and you're also dealing with very large pathways. All right, so if the heuristic function is not very accurate, then clearly the greedy search is not going to be very good, because the greedy search really relies on that heuristic function. It relies on a function that is already a good educated guess about optimality. So stated here, sometimes it can return the most expensive path. And there are actually better methods than this. So the next method I'm going to talk about is what's called the A-star search algorithm, which is much better than the greedy search if we actually want to arrive at optimal pathways. There are other kind of problems that occur with greedy search. So if, for example, we're at a node and the edges to the children all have the same weight, we actually arrive at a position where the search doesn't have any information. The greedy search can't know about any other pathways beyond these two children because of the way the heuristic function works. So it doesn't have any information about which choice to make. It has to do something random here, like put it in some either priority, standard order or some kind of random order. So this is one of the fundamental flaws of the greedy search. Alrighty, I'm going to give us a break now because it's about 10 to 11. So I'll come back at 11 o'clock and then I'll talk about the A-star search algorithm. And I think I know what. Alrighty. So just before the break, I was pointing out that we have this real kind of problem with greedy search in that sometimes it really doesn't have information. So there can be cases in a graph, a weighted graph, where actually the search has no good information on making a choice. Right, so given that case, how can we actually improve our heuristic function? All right, so I'm going to suggest an improvement, but I'm also doing it with certain intent, and that is that I want to arrive at a heuristic function that is the one that's being used for the A-star search algorithm. So we can improve things. What we can do is we can have a record of how much it's actually cost to get here, and also having an estimate of cost to the goal. So what we were doing before with the greedy search was we were just simply relying on the heuristic function to make a choice of siblings or a choice of neighbourhood. Now what we're doing is asking for a heuristic function that makes a guess about the cost from this node to the goal node, which is entirely different. So we could have a heuristic function like this for, say, algorithm A, and it's a function fn where gn is the actual cost it took to get to a certain node, and hn is the cost it'll take to get to a goal node. Right. At this point, I'm going to deviate drastically from the fundamental greedy search approach. So far, we've been talking about a search that is a depth-first search, okay? It should be fairly clear from this algorithm because it's recursive and because it has a base condition that this is a depth-first search. It goes down to a certain base condition. If a child has been painted, it should also actually say if the child is an edge. But if the child has been painted, or if the child is a goal node, then it returns. So that is basically, it's going, in a tree structure, it's basically depth first. That is, it's going down to a certain depth, and it comes back up, and it searches like this. Okay. For what I'm going to show you next, we're going to be dealing with what's called a breadth-first search. That is, it's a search that starts looking at the first layer of all the children of the first layer, and then all of the children down to the second layer, and so on, or all of the siblings down to the second layer. And this is really where this kind of heuristic becomes useful, because we're also keeping a cost of a record of the actual cost to get to a certain node, and what we're trying to do here for this algorithm A is we're trying to get an algorithm that takes the best of both worlds. It takes the best of the depth-first world and tries to also take the best of the breadth-first world, or the best breadth-first approach. So it tries to strike a balance between going deep and going broad. That is, it tries to strike a balance between exploitation or exploration. Okay, this is a fundamental dichotomy in artificial intelligence, is this idea of exploration, which is the breadth of your search, and exploitation, which is the depth of your search. When we do a search like this, we also want the search to be what is called admissible. So if we're actually after an optimal pathway, that is, we're after the shortest path, we have to guarantee that we admit all possibilities into the search. That doesn't mean that we have to search every pathway. It just means that we've admitted everything that is logically necessary in order to find that shortest path. So a search algorithm is admissible if it is guaranteed to find a minimal path solution wherever such a solution exists. So, for example, a breadth-first search is always admissible. A breadth-first search is admissible because, you know, if we have a tree structure and we have some goal that's here, we might also find that there's a pathway with the goal here, but it's a much longer path. If we're going breadth first, we'll find this first before we ever get down here and find this one. So it admits all possible pathways because it's breadth first. And having stated that, once it's found the shortest path, it doesn't need to look at all of these other nodes. It's only looked at all of the nodes within a certain depth. So that's an admissible search, but it didn't have to look at all the nodes. Yes?
This must be a little bit pedantic, and correct me if I'm wrong, but I thought that definition was for optimal search, whereas admissible is like when a heuristic never overestimates the cost.
Wherever such... Well, in this case, because...
Or is admissible like the same as optimal?
No, admissible simply means that we admit all possible solutions or all possible pathways into the search that's necessary. I think that you're probably right. It is really talking about optimality here. If it's guaranteed to find an optimal path, that is actually the end result of admissibility. It's true, but I get your point. It is probably, yeah, it's probably not well stated. Right, so as stated here already, a breadth-first search is absolutely admissible. As I pointed out, once we get to that level and we found this pathway, we don't have to look at all of these other nodes, so it's not a brute force search. And yeah, as stated there, it looks at every node at level k before it looks at every node at level k plus 1. So if we want to find shortest paths, then we want a heuristic function that will give an admissible search algorithm. Now, notice that I'm talking about a heuristic function that leads to an admissible search algorithm. The reason why I'm using this terminology is because there is a certain development for the A-star algorithm that comes out of firstly, the development of the heuristic function. And it works like this. So let's assume that we have this function f star n. As I already stated before, the problem with search functions is that we don't know the optimal solution before we start the search. Okay, we don't have that prior knowledge. If we did, we wouldn't need the search function. Similarly, we don't have the optimal heuristic function. All we have is some suboptimal function which we hope is a good function. So what I'm doing here is I'm making the assumption, let's assume that we already have the optimal function. Let's assume that. So assume that we have this function f star n, which is equal to g star n plus h star n. And it's optimal. That is that g star n is the actual cost of the shortest path to the current node n, or it should say along the shortest path to the current node n, and h star n is the actual cost of along the shortest path from the current node n to the goal node. So f star n would be the actual cost of the optimal path. We refer to this kind of function as an oracle. So it's a kind of tool or a way to characterize a problem and a solution, or it's a kind of way to characterize a solution that we don't have, and then try to fashion our approach around this fantasy function. So what we want really is a heuristic function that begins to approach this fantasy function. You know, we obviously already know we can't get f star, but we want a function that comes close to it. Right, so in algorithm A, if the search is good, then the function dn, the actual cost of the path to the current node, is already a good estimate of g star n. Okay? So we can already say that whatever it's cost us to get to a certain node in the search, it's either going to be bigger than, that cost is either going to be bigger than or equal to our optimal function g star n. Remember, we don't actually have this function. This is just what we would like to have. But we can define conditions, right? Because we know this, we can define this condition around this oracle. We can say, well, our gn has to be either bigger than or equal to it. We're either on the optimal path, or we've made a mistake somewhere and we're not on the optimal path. It's a bit longer than it should be. That's really what it's saying. So given this above property of Gn, our algorithm would be admissible if and only if we enforce another condition. That is, our Hn, our estimate of cost to get to the goal, is less than or equal to A star, H star n. All right, so we've imposed this condition. This condition isn't solved yet. This is the condition that we need to make sure is maintained right throughout the search. So we're actually searching on that condition that Hn is less than or equal to A star n. Notice, and I'll bring this up again. If Hn was always 0, then we would have a breadth first search. I'll point that out in a moment. Okay, so the A star search algorithm is just algorithm A, where we're using the heuristic function fn equal to gn plus hn and applying that condition that hn is smaller than and equal to our oracle. Now, this is doable in many situations. It's not always doable. We can't always come up with a function like that. Oh, yes, we can. We can always say 0 and just do a breadth first search. So yes, we can always come up with a function like that, but that's the trivial case. We want to have a function that is more useful than that. We want to have something that is smaller than and equal to A star n, but is really close to A star n as well. So we actually want this function to provide us some information, where the number 0 being a constant doesn't provide us really any information. So What we can do in Euclidean space is simply use if we're talking about pathfinding, simply use the distance, the direct distance from the current node to the goal node. That's always going to be smaller than or equal to our h star n. All right. So the actual distance between the two vertices as a Euclidean distance would satisfy for pathfinding. All right, so how does the A star search work? So let's again assume that we have a graph where we have weights representing distances. So this is just a mock-up. It's not a real one, but it serves a purpose for our example. So what we can do here is that we can assign for each of our child nodes, we can assign an evaluation based upon that heuristic function fn. So we let hn1 equal the length of a straight line from node n1 to the goal node, and we find that that's 1.4 units, so this is just a mock-up. That doesn't sound right. There should have been a 0. Oh, no, that's right. Oh, it should have been a 0.1. Anyway. Okay, yes, no, that makes sense. So this might be a distance, direct distance from the root to the goal would be 1.5 units. But from here to the goal, it's 1.4 units. That's not saying that should be the value 1. It just simply means that that the distance from here to here is 1, somewhere about there. Okay, so what we're doing here is that we do a calculation. We're going to be evaluating all of these nodes with evaluations from that heuristic function. So the search begins at the root and expands it and evaluates each child. And so we compute that function. We take 0.3, which is our GN, the cost to the current node, plus 1.4, which gives us 1.7 for that one. Again, this edge is 0.2, and the straight line is 1.3, so we get 1.5 for that one, and so on. So each of these get evaluated with a value from the heuristic function. Now, unlike the greedy search, we're not doing a depth first here. We're actually kind of doing a breadth first. So we want to keep all of these nodes open, and we want to be able to search on them in a random way. So we want to have random access to all of these nodes. And then we want to be able to exploit that heuristic function randomly. So basically the heuristic function is driving the search and driving the order in which these nodes are being searched in the open set. So we need basically that. We need an open set or a data structure where we can have all of these nodes open that are coloured red. So the nodes in red form what is called a frontier. Basically, A star kind of forms a frontier and keeps picking nodes off that frontier until it comes up with an optimal pathway. So the nodes form a frontier, and this frontier is what's called the open set. Then we also have what's called the closed set. That is the nodes that we're no longer searching. We don't need to search the root anymore because we've already looked at all of the children of the root. So that has been put into it's been coloured blue, and it's been put into the set, the closed set. So we have these two sets, the open set and the closed set, and basically the search is always searching from the open set. All right, so given this image and the evaluations assigned to the node, A star is going to choose one of those out of the open set, and it'll be the one with the cheapest evaluation of the heuristic function, and that's this one with 1.5. So it'll choose this node, and then it'll expand it. And by expanding it, it again looks at the children of that child and evaluates each of those children, and then puts those children also into the open set. So now what you can see is that we have actually 4 nodes that are in the open set. So here we had 3. We chose to expand that node. These 2 still remain in the open set, and these 2 new children are added to the open set, and now we've got 4 nodes in the open set. These get evaluated, and then A star will then choose from this set the cheapest child, or the one with the lowest evaluation, and that will be this child here. So notice what A star is doing. It expands a child if it can exploit that information, but the moment that it finds the moment that it finds its heuristic function is not performing well on the children of that, then it doesn't need to choose those children. It can choose the children from the previous node if it needs to. So this is what I mean. It's going to do some random selecting of nodes from this open set until eventually it finds the shortest pathway. And this is a very, very effective way of searching because, for example, this node here could have children, and this node here might have other children, but in fact the shortest pathway might be along here, and so it never had to expand any of these children. It could immediately expand from here from the beginning. Basically, as I pointed out, it's trying to take advantage of both depth first and breadth first. So A star tries to create a sort of frontier that isn't flat like a breadth first, but kind of does some exploitation in order to get to its optimal pathway without having to do too much exploration. Right, so it continues in that pattern. It continues to expand children and expanding children, evaluating them, and selecting the optimal one until eventually it arrives at a pathway. And then it does a parent-wise backtrack to record the path. That is, once it gets to the goal, it asks what was the optimal parent from that goal, and just steps back and then returns the pathway. Now, as stated before, if HN is 0 always, then A star does a complete breadth first. Right, so this is not a recursive function. This is a while loop, and it's a while loop because it's doing essentially a breadth first, which is guided with the heuristic function. So again, we're taking the root and the goal as our input, and we want to return a path. And we have the open set, which is initially given the root, and then we have the closed set. Remember, the open set is the set that A star is searching from, or it's expanding nodes from, and the closed set are those nodes which A star is no longer exploring. So it says while there is a non-empty open set, let's do this loop. And so it looks at all of the nodes in this open set and it pops out the best one. So that'll be the one that has the best evaluation. And then it puts that immediately into the closed set. And then for all of the children, it evaluates those children. And if any of those children happen to be the goal node, then we've finished. We've found the goal, so that then we can return the path. In which case we do a parent-wise backtrack and then we return that path. If not, then another query has to happen. The search has to ask, is this child, if the child is not in the open set, and if the child is not in the closed set, then we put it into the open set. So the reasoning here is that if it's already in the open set, we don't need to add it again. And if it's in the closed set, then we shouldn't be, actually we shouldn't have it anyway. It should never be in the open set to begin with. Okay, so, and then there's also a fail case, but this is just a simple while loop, and that's how the A-star algorithm works. It just simply goes through this while loop and selects nodes from the open set based upon evaluation. All right, so what is unique about the A-star search as opposed to greedy search is that it is guaranteed to find the shortest path even in a very complex graph. So it's good for finding shortest paths in games where NPC are racing around very complex environments. It's good for mazes. So there are different environments and different conditions whereby the two algorithms are better. The A-star is really good when you have a lot of bends and turns that you need to search through. So for example, in a maze, A-star is really good in mazes. So, you know, because there is all of this bending and turning, and sometimes the pathway is going in an opposite direction to the goal, the A-star will return an optimal pathway in this environment, which is often desirable. In this environment, however, the greedy search could easily search the entire space and not find an optimal solution. Oh, yeah, or find, yes, that's right, and might actually find the worst solution. The greedy search is actually not a bad idea, though. It's much faster than A-star. It's faster because it's committed to a best first search. Okay, it's unless it has to backtrack on a few dead ends, it's absolutely committed to doing a best first search till it gets to the node, and that's what makes it so fast. It's good if you are in an environment where it's very easy to see there's a lot of fairly straight sort of pathways. So in a forest area like this, a greedy search would be much better than an A-star search. So the problem with an A-star search here is that it's going to be looking at an open set and picking from an open set as it goes along, where with greedy search, as I pointed out, it just simply chooses the next best option without having to look at any other children. Now, as stated, if you don't care about the pathway being optimal and you've got an environment like this, use the greedy search. It's way faster. Okay, so I'm going to sort of talk about a few conceptual concepts here. First, I'm going to talk about navigation meshes, but in particular, I'm going to talk about ways you know, that you might be able to reduce the search space for your pathfinding. These kind of optimizations, you know, they may not be necessary for pathfinding. I think pathfinding in game engines is pretty much solved. But the concept of what I'm showing here is useful in other kinds of searches. So a nav mesh, again, can be generalized to some graph. And the way that we do it is that we think about the polygons along a nav mesh. Is everyone familiar with what a nav mesh is? So often in game engines, the way that we do pathfinding these days is that we consider the collision mesh. So in any environment, say a floor or a mountain ridge or whatever, you have basically a collision mesh. And that collision mesh is used to decide if objects have collided with it. It's a fairly broad structure. It's a fairly rough structure. It doesn't have the same level of detail as the object that you're trying to represent. So you might have some object that has millions of polygons, but the collision mesh might only have, you know, a couple of hundred. But collision meshes are really good also for defining navigation meshes. So often in game engines, we take a collision mesh and immediately generate a navigation mesh from it. And so a navigation mesh is really a mesh made up of polygons, and this is a fairly reasonable example of a navigation mesh. And this can be converted into a graph also if we consider the center point of each of these polygons and the adjacency between the polygons as edges. So immediately we have a kind of graph concept here. Now the idea here is that we have some reference point on the polygon, and so if we have a character that's moving along these polygons, you might want the character to either pass through these points or maybe just coming close to the points as it's moving along the surface of the polygons. All right, so given that graph, a search in G would then return a pathway like this. But part of the problem here is that we might need to actually describe more detail about it, or we might want to be able to make some sort of decisions about the search before we get this pathway. So there's a few things that we might be interested in doing here. We don't necessarily want our characters to always run along the same path each time. Once we have this set of polygons as our pathway, we actually have a lot of space and a lot of surface area for this character to move around. We might like our character to move along a smooth pathway. So part of the problem with this is that if our character is moving along these points and you're just going along straight lines, it's not going to look very natural. The character will look as though it's running, it's obviously going to look like it's running along straight lines. So one thing that can be done here is that we can use Bezier curves in order to smooth out the pathway. And so these Bezier curves can be defined along each of the junctions between the polygons. So we just simply choose a crossing point that crosses the edges of these polygons, and then we find control points at the end of tangential lines, that is, lines that are perpendicular to this edge, but tangential to the curve. That's why they're called tangential lines. And then derive Bezier curves from the control points. Now, part of the problem with Bezier curves, if you're familiar with these, is that they don't have continuity. So you don't have continuity between a curve from here to here and another curve going from this point to this point. And this will be important for animation purposes. So Bezier curves are basically a class of parametric functions like this ft, where t is a scalar between some values 0 and 1. The problem for Bezier curves is that when you stick Bezier curves end to end, they're not continuous. So what happens is, if you're moving a character along this pathway based upon this parameter t, then it's going to maybe move faster along this curve, slower along this curve, but much faster along this curve, because our parameter is in a range from 0 to 1. So if you're scaling through, if you're ticking through values between 0 and 1 for your parameter t, then it'll go, it'll take longer to get from these 2 points, which are actually closer together, and much shorter time to get between. It'll take the same amount of time in each case, but these 2 points are closer together and these 2 points are further away. So the character will appear to move slower here and then much faster along this part of the curve. So we have to try to solve this continuity problem when using curves in order to smooth our paths. As stated, it might be the desired effect, so that's being a bit optimistic. Alternatively, we can use what's called Catmull-Rom, which is a set of curves that preserve continuity. Again, with these splines, there's how do I put it? So with these splines, you know, we can ensure that as we go through each point, we actually have continuity. That means that we can use this parameter in order to position our character along that pathway and ensure that the character is moving at the same velocity as it goes along that path. All right, so the way this works is that we actually consider... so the tangent at each point pi is calculated using the previous and the next point in the spline. So basically this tangent is parallel to this line, this tangent is parallel to this line, this tangent here is parallel to this line between those 2 points, and so on. And that's how it preserves continuity. Okay, the other thing that we might want to consider is actually, something to do with the size of the character that we want to move across this surface. And that can be important in making decisions about whether that pathway should even be used or not. So if we think about a pathway, you know, it might be sufficient if we've got a fairly skinny character to move along this path, but you might actually have a very large character or object. You might have a massive tank, and it's not going to make much sense if your tank has calculated a pathway and it's going to drive along a surface that is far too narrow for it. So we can include ideas like resistance. So an edge in a navigation mesh offers some resistance to the flow of an NPC. So if the NPC is smaller, then the range of possible points that it could pass through is quite wide. However, if the NPC is very large, then the possible places where the NPC could move across a boundary is very narrow. And in fact, if the NPC is too wide, this threshold might actually be, you know, you might actually calculate it as something that's 0 or negative, indicating that, in fact, your object could not pass over that way. So stated here is, if the NPC is really big, then we could use the fact that our NPC has a certain size as a way to eliminate certain pathways in our pathfinding. So that could be other information that we add to our search algorithm in order to eliminate or to reduce the amount of searching that our algorithm has to do. So you can see one of the key aspects of thinking in this way, or thinking about artificial intelligence, is always looking for ways to reduce your search. What other ways, how else can we think about the problem in order to make the search more efficient? Okay, so we also might want to look at the surface area in a navigation mesh. It might be that we already have objects on the surface that we're not even considering, and we should be considering. So let's say our polygon already has a bunch of stuff on there, like, I don't know, trees and buildings and other rubbish, you know, that you couldn't really drive a tank through, or you could, or you couldn't really walk a character through. Or there might already be other characters standing on this polygon. So given that, you know, it wouldn't look natural for your character to walk through a crowd, essentially walking or trying to walk through the other characters that are standing there. So we might want to think about capacity. So if NPC occupy only a small fraction of a polygon surface, then more NPC can be added, or more NPC can move through here. If NPC occupy a large fraction of the polygon surface, then really fewer NPC can be added to it. And that can also be used to decide whether your pathway should go that way or a different way. So again, polygons can be eliminated from any new path search if we expect their capacity will be depleted by the time the NPC arrives. So this is sort of taking into consideration the idea that we're working with a game that's got a sort of fairly dynamic environment. We've got other characters that are around. We might actually have players with their avatars that are in there as well, and that might actually affect whether an NPC could pass over that polygon or not. The other thing to do, is to consider how to make the character appear to be flowing over that surface or walking over that surface and looking natural. So if our character always looks like it's going directly in the middle of these edges on the polygon, it does two things. First of all, it exposes the fact that there's a polygon mesh there. And secondly, it doesn't look natural that your character is always following the same locations in its path. So one thing that can be done is if we consider this threshold or this edge between polygons, and we consider maybe a normal distribution, and then use a random number generator to select randomly points along this edge as the threshold point or the throughput point where the character is going to move across it. Yep, so this is where we could just randomly choose control points, just to make the entire animation look natural. I think, didn't we just cover grids already? All right. Oh yeah, okay, so grids, which are really just a generalization of navigation meshes. As I already pointed out, it's naturally derived from the Euclidean space. Since grids are a special form of navigation mesh, grid elements can have resistances and capacities, just as we've discussed for navigation meshes. Stated here, they can be chosen dynamically. I think that's right, I've got a hierarchical approach. Okay, so how can we derive expected grid capacities, allow obstacles in the environment to consume capacities of the grid element? So we're saying that if there are other objects in the environment, then we use that as information to decide whether we want to include that grid element in our pathfinding search or not. So we can let a function En be the expected capacity of a grid element. So En is simply 1 minus the full capacity of that element. So 1 minus how much of that element is actually consumed divided by the full capacity of that element. And this then gives us the expected capacity, how much or how many other characters could possibly fit on that element. So we could then just use that function in a really simple way. We could just use it as a yes-no kind of function and say, well, we'll exclude grids. If it's 1, we'll exclude the grid. If it's 0, we'll include the grid. Yeah, so in this case, ignore any child grid element n where En is greater than some predefined value, or we might be able to linearly combine En into our search heuristic function. For example, we could extend the A-star search. We could create a function like this where W is an empirically chosen scalar depending on how much we want to include this evaluation into our heuristic function. All right, so the idea that I was developing there, I know it's a little bit sketchy, but it's about trying to do pathfinding in a hierarchical way. So hierarchically, we might be able to consider objects in a kind of statistical way and do some sort of search evaluation to decide on a pathway at a really high level. So the idea here is that I have a game environment. I've divided it up into a very coarse grid, and then I look at each element and I look at all of the stuff, all of the different obstacles that are in that grid space. And then I do an evaluation. And so that's where this En comes in. That En is a measure of how much capacity for a pathway is given in each of these elements. So there's already a pathway. There's a couple of pathways already on this ground plan. There's a pathway that goes along here and another one that goes in this direction. So we have a start location here and an end location here. So this evaluation would have already ruled out all of these squares simply because, you know, there's all water and objects here and no pathway. There's no pathways here. There is a pathway here, so it would have included that one and that one. But because our 2 points are between here and here, when we do a simple, even just a simple greedy search, we end up with this L-shaped set of grid elements. So this is just the first path. What we can do now, because we have this L shape, is that we can eliminate all of these other elements from the search space. And then we can do a second pass. We can use exactly the same function. We can look at how much stuff is in each of the cubes, in each of the squares. For example, this one would give an evaluation where there's 0 capacity. This one would have some capacity because there is a pathway there, maybe a little bit of a pathway here. But the rest of these squares would have 0 capacity, in which case the search would only consider maybe this square here and maybe this square here as additional squares. But again, when we do even just a simple greedy search here, we end up with this pathway. And now we can throw out all of these squares, and then we can do another pass, and so on. So hierarchically going down, we can end up with a very efficient pathfinding algorithm just based upon these kinds of statistical evaluations of stuff or capacity on the grid elements. Eventually we get down to a level where we're happy with the grid elements. So clearly you can see we can continuously refine this until we get down to the level of the pathway itself. There are some problems with this approach. We might choose a grid element like this one, but here we have an edge of the grid that is sitting right on top of the path. What we want to be able to do is we want to be able to maybe choose both of those at the same time. Because we have this problem where we have the edges of the grid which is sitting directly upon the path. What we really want to do ideally is to, you know, either have all of the pathways lining up with the grid elements, or we want to have some way to evaluate both of those simultaneously. So there is a problem with this hierarchical approach. One neat thing about the hierarchical approach, though, is it's really quick. We don't have to use A* all the time. We can use something really simple like greedy search, which is a really fast search. Okay, so that pretty much wraps it. Next week I'll show that video. I don't think we need to show it now. All right, so next week in the workshop, not this week. This week is the rotating cube for those who haven't used Unity 3D. But next week we will actually implement in the workshop the A* and the greedy search pathfinding algorithm, and that will get everyone onto practical implementations of a search method. Next week in the lecture, we'll be looking at, in the architecture, we'll be looking at the simulator and the controller software. We'll be looking at agents in particular. We'll be looking at perception and reactive agents. We'll be looking at adding some control features such as scripting simple behaviours, using events and triggers. But our main feature of next week will be this reactive agents. And then we'll be talking about what's called state machine agents. Okay, so that wraps it up this week, and I'll catch you all next week.